So this video is going to be on the 6th lesson, practicing solving log and exponential equations, and particularly looking at application of exponential functions. So the lesson first starts talking about the difference between exponential growth and exponential decay. So exponential growth, if you remember back from grade 11, looks, if we do, for instance, let's say y equals 2 to the power of x, when x equals 1, we're going to be at 2, x equals 0, we're at 1, x equals 2, 2 to the power of 2 is 4, x equals 3, we're going to be up at 8, and so on. And then negative 1, we're at a half, a quarter, an eighth, and so on that way. So we get a horizontal asymptote going to the left, getting closer and closer to 0 as x becomes closer to negative infinity. So, and this happens when the base is greater than 1. Let's generally use b for base. B is greater than 1. For instance, if we have a 22% growth rate, that corresponds to a base of 1.22. So our base is 1 plus r, where r is the growth as a decimal. Up here our base is 2. 1 plus 1 gives us 2. So this means we're going up 100% each time. If we're doubling each time, we're going up by 100% for every x. 22% of x, we're going up, our base is going to be 1.22. Exponential decay looks the opposite. So for instance, if I do y equals 1/2 to the x, that's going to be basically flipped over our y-axis going this way. 1/2 to the 1 is 1/2. 1/2 to the 0 is 1. 1/2 to the negative 1 would be 2. 1/2 to the negative 2 would be 4. So we get that same sort of shape. So base is positive but less than 1. So it's between 0 and 1. And then if we depreciate by 15%, we're decreasing by 15%, we're subtracting 0.15, 15%, and that equals 0.85. So for depreciation, it's 1 minus r. So overall, we get an exponential equation. So our general exponential equation, hopefully this is familiar. Y equals a times b to the x. A That was like our initial value, our starting value. Whenever x is 0, we just get an a there. B, the base. And so this is basically like our growth or decay rate. It's the portion of the sample that is present. How much is there after one cycle? X, number of cycles. So if we go through 2 cycles, we're going to have this much, this B amount after this one cycle, and then again after the second cycle. And then y is our final value, or how much we end up with after going through X number of cycles. So grade 11 used this to solve different problems related to growth and decay. I'm not going to write down the problems just because they're fairly lengthy, so you can look back at the blank note that's posted to refer. But in example 1, in 1987, the world population reached 5 billion and was increasing at the rate of approximately 1.6% per year. If we assume that this growth is maintained, we can write an equation expressing the predicted population p billion as a function of the number of years n since 1987. So we're starting in 1987. So we can look at our general equation, y equals ab to the x. If we're increasing 1.6% increase per year, that's telling us that our b has to equal 1.6% as a decimal is going to be 0.016. We divide by 100, or 1.016. If we're going from 1987 to 2016, that is 29 years, so 29 cycles in this case, because that 1.6 was happening per year. And so I guess I'll have to go back up here. So we want it as a function of p, because it asks us to write as p billion. We started off, our initial value is 5 billion in 1987. It's because this function's talking about billions, we're just going to write 5. Our base was 1.016, and then our function is n. So then, if we look at p of 29, so we're looking for 2016, 5 times 1.016 times 20, or to the power of 29, sorry. Take out our calculator. 5 times 1.016 to the power of 29. And we get, that is not right. Oh, there we go. 7.92. So about 7.9. So therefore, this prediction, there will be approximately 7.9 billion people in 2016. So we'll look at another example here. Example number 2. Oh, I guess I can turn this side over. So example 2, on each bounce, a ball rises to 70% of the height from which it fell. Suppose the ball originally fell from a height of 2 meters, we can calculate the height to which the ball rises on each successive bounce. Write an equation that expresses the height of the ball after n bounces. Find the height of the ball after 3 bounces. So every single bounce, so this is example 2, every single bounce, we're 70% of our previous bounce, so this is an example of exponential decay. It already tells us what happens after one cycle. We're at 70%, so our B is going to be 0.70. Every cycle we go through, our height is going to get multiplied by 0.70. Our initial height was 2 meters. And we're interested in what happens after 3 bounces, after 3 cycles. So we can set up our equation, I guess. Yeah, we'll do h for height. That's what's in the notes. H of n equals ab to the power of x. So h of n equals 2 times 0.70 to the power of 3. And if we calculate that, we get 0.686. So after 3 bounces, the ball's height is 0.686 meters, or you could say 68.6 centimeters. Question doesn't ask for the height in a specific unit, so in that case, up to you. We looked at stuff, or I guess in grade 11, you would have looked at stuff that was a little more complicated. So let's look at example 3. In favorable breeding conditions, a colony of insects can multiply tenfold every 3 weeks. If there are now 500 insects in the colonies, express the number of insects n as a function of the elapsed time w, and then calculate the insect population after 25 weeks. So again, we're looking at our standard exponential equation. The only difference is now a cycle isn't a single unit of time. Every single cycle is 3 weeks that we're looking at. And we're going through 25 weeks. So our exponent, 25 weeks, we want to see how many cycles of 3 weeks that is. We're going to divide by 3. So 25 over 3 is going to be the number of cycles we'll complete. And we can use that to create our equation here. So it asks for a function n in terms of w. Our initial value, we had 500 insects. And we're multiplying by 10. We're multiplying tenfold every cycle, every 3 weeks. So the only difference in this one is now we have a fractional exponent because our cycle isn't just a unit time. Last one, it was every bounce. The first question, it was every year. Now it's every 3 weeks. So that's kind of the added wrinkle here. And then from there, once we have our equation set up, we're still just calculating it. We can plug it right into our calculator. Oh, I punched that in wrong. 500 times 10 to the power of 25 divided by 3. We get, wow, 1.08 times 10 to the 11, or that's approximately what? Followed by 9 zeros. 2, 3, 4, 5, 6. So what? 108 billion insects after 25 weeks. Magic of exponential growth. So for these problems, we can rewrite this as a slightly different equation. We can use y equals ab to the power of t divided by tc. So still we have, this is our final value. This is our starting value. B is our base. So we're either using that 1 plus r for growth, 1 minus r for decay. And then this whole term is our number of cycles. T is the entire time that we're doing this for. TC is the time per cycle. And so by dividing those, that's telling us that number of cycles. So it's really just the same formula we've been using in disguise. In grade 11, you would have always done this where you knew how many cycles you were completing. You always knew what your exponent was. And that's because in order to solve for an exponent, we need to use logarithms. So now that we're introducing logarithms this year in grade 12, we can solve a problem like this where we don't know the number of cycles that are being completed. So I'm going to look at, again, these are in the blank note. Feel free to bring it up if you're watching this video. Like split your windows and then you can follow along. But this question is saying a rabbit population can double every 3 months. So 3 months, that's going to be one cycle. So the time for one cycle is 3 months. And if the population's doubling, that means our base is going to be 2. We're multiplying by 2 every cycle. How long will it take a colony of 45 rabbits? So our initial value is going to be 45. And our final value, we want to reach a population of 400. So we can set up our equation that we just talked about. This y equals y equals ab to the power of t over tc. And we're going to sub in what we know. And we don't know what the total time is, but we do know the time for one cycle is 3 weeks. So 400 equals 45 times 2 to the t over 3. We're going to get rid of this 45 on this side. We'll have 400. We'll divide both sides by 45. So we just have the exponential. And then we've done a lot of going from log form to exponential form. This time we're going to do the opposite and go from exponential form to log form. So our base of our log is 2 because the base of our exponent was 2. This 400 over 45 becomes the argument for our log, and t over 3 is what that log is equal to. Well, now we have a much nicer looking question. We don't have a t stuck in an exponent. We have t all by itself. We just need to multiply by 3, and we're going to get t all on its own. So I'm just comparing to what we have in the notes. So this is different. This is an alternative method to what we have in the notes. In the notes, they've just simply taken the log of both sides. We can change this to a log base 2. It just means we have to do one more step before we calculate. So you'll see that this actually goes back to what is in the notes. This is a slightly different way to look at it. But in order to calculate this in our calculator, we have to do the change of base. So the change of base, we're doing the log of any base we choose, so base 10 because we want to put it in the calculator, log of our argument, 400 over 45, divided by the log of the base. So if you compare this now to how they've done it in the notes, this is the exact same. This gives us the exact same result. We just had some different steps, intermediate steps. But again, if we put this in the calculator, we'll get exactly what we have in the notes. 3 log 400 divided by 45. And all of that is divided by log 2. That gives us t is approximately equal to 9.46. So was this question's rabbits per month? So the rabbits reach a population of 400 after about 9.5 months. 9.46, 9.5. Either way is okay. So that's our first example looking at solving a question with logarithms. I'll show you, I guess, taking the log on both sides in the next one. But either way you do it is fair. You can turn this into a log base 2, and you're going to have to divide by that log 2 eventually anyways, or taking the log of both sides gets us to this as well. So let's move on to number 2. If the population of a colony of bacteria doubles, so if it doubles, our base has to be 2. If it's doubling every 30 minutes, so it's completing a cycle every 30 minutes, how long will it take the population to triple? So we want whatever our final value to be 3 times our initial value. So if we plug this into our equation, so our final value is triple our initial value, our base was 2, and TC, time for one cycle, is 30 minutes. We have 2 variables that we don't know. We have A and we have T, but if we divide by that initial value, divide both sides by A, we're going to cancel out that A anyways. So we don't care what the final population is. We don't care what the initial population was. All we need to know is that it was some factor times the initial population, and that allows us to fully cancel out A. So 3 equals 2 to the T divided by 30. Again, we could turn this into a log base 2, but we'll go the other method here. We take the log of both sides. So as long as I'm doing the same operation to both sides, it's fair game. And if you're using this method, the way we get t out of the exponent is now using our log rules, our power rule. We can bring that t over 30 out in front, and we get t over 30 log 2 equals that log 3. Can divide this by log 2 to cancel out that log 2, and multiply by 30 to give us just t on the right side. So t equals 30 log 3 divided by 2. 30 log 3 divided by log 2. That gives us about 47.5. So the population of the bacteria will triple after about 47.5 minutes. So again, we don't need to know anything about the initial, well, not anything. We don't need to know the exact value of the initial and starting values. We just need to know their relationship. And if we do this method, we never have to do a change of base. The change of base comes from the fact that we took the log of both sides. So we get everything in log base 10 already, which will allow us to put in our calculator. So whichever way you feel more comfortable with, that's the way you can use. And finally, we have one more question here. A research assistant made 160 milligrams of radioactive sodium and found that, okay, so our initial value, we're starting with 160 milligrams, and found that there was only 20 milligrams left. So Y is 20 milligrams, 45 hours later. So total time is 45. What is the half-life of Na24? So again, half-life is, that's the time it takes to reduce a sample to half its original mass. This is used a lot with radioactive materials because they don't hold their mass. Reduce sample to half its original mass. So in that case, we're interested in B of a half. We're interested, I didn't need brackets there, but we're interested in how long does it take to have half of what we originally had. So we can look at a B of 1/2. We plug this into our equation. We have a Y value of 20, A initial value 160, half-life, total time was 45, and we want that TC. We want to see how long does it take to get a half-life. So the time of our cycle, time of a half-life, we're going to divide both sides by 160. So we get 20 over 160 equals 1/2 times 45 over TC. 20 over 60. Right away we can see 2 over 16 or 1 over 8 equals 1/2 to the power of 45 over TC. So we could solve this without logs. We could see that 1/8 is the same as 1/2 cubed, and then we can equate our exponentials. But I'll keep doing this with logs just so we can continue seeing this. So I'll revisit that first method we looked at just because that's not in the notes. So if we're turning this into a log, the base of this exponential is 1/2. And this way you can see stuff with fractions in the base of the log. Just get a little more exposure to that. Our argument comes from the side that was all by itself. The y value of our exponential, or the y value of this exponential. So 1/8 is going to be our argument, and then the exponent in the logarithm is now all by itself. 45 divided by TC. Log 1/2 divided by, log base 1/2 of 1/8 is log of 1/8 divided by log of 1/2. If we change the base, equals 45 TC. We can cross multiply. So TC times log 1/8 equals 45 log 1/2. And then divide both sides by log 1/8, and we get TC is 45 log 1/2 over log 1/8. We put that in the calculator. 45 times log of 1/2. Careful and make sure you use brackets around your argument, or else it's going to take the log of 1 and then divide that answer by 2. And we're dividing by log of 1/8. Again, careful, use brackets. So all of that equals 15. We had done this other method, and so 1/2 cubed. We equate our exponents and rearrange, get 45 over 3. We would also get 15 that way. It's just like an extra check. Therefore, the half-life is 15. This was minutes. Yeah, no, hours, was it? Hours, 15 hours. I guess I should have written that down originally. 45 hours. So our half-life is 15 hours. So that's the end of this chapter. Again, don't hesitate to ask any questions, but I hope everything's well with you guys. And you'll hear from me again in the next lesson. Bye.